for both lectures, so we'll see. I have no idea why that stopped. Can you guys see the slide? Okay, yeah, sorry about that. I have no idea. Okay, let me see. Okay, pen's working. Okay, so I was saying, let me see, where am I at? Yeah, that, I think you guys are going to get into part 3 in lab tomorrow, and a big part of that is trying to determine and measure the instrument response function in the lab. And previous lectures, we said a great way to do this is to send in a direct delta function. And we defined, when we were talking about Fourier transforms, that a direct delta function will be infinite in height and infinitesimally small in the length or the time. And we can't achieve that in the lab. So this is what you'll be using instead. You want something that's going to be as large of magnitude as possible. And I'll say this as a conditional, that you can't just send 100-volt signal through, that it's also, of course, important to make sure that you're not going to break the instrument, so without overloading any of the instruments. And then you want this to be shorter, so this is your y-axis value here. And then in your x-axis, you want this to be shorter than the characteristic time. So when we're talking about the low-pass filter, your time constant of your filter, circuit, or instrument. So you should have some rough idea of what your characteristic time should be if you constructed the circuit yourself. So you can guess, or you can at least approximate and choose something that is comfortably lower than that characteristic time. Of course, you would, when we're saying infinitesimally small, you can be like, oh, I'll send a nanosecond pulse through. But if it's really, really extremely short, you're not going to get any output. And that has to do with, again, thinking of the convolution and showing that shift, that animation I showed earlier. If it's extremely small, your output is also going to be extremely small, and it might be below the detection limit of your detector. So that's what I mean by no output, like below the detection limit. Of your detector. So in lab tomorrow, you're going to have an idea of what the characteristic time is. So you should be able to have a well-informed choice. But also there's times where you'll have some commercial instrument. It's not something you built, and you don't know what that characteristic time is. So a better way there would be to do a large range of widths or large range of times in your square wave pulse that you're sending through. And when I mean a range, usually the best way to do this is do like order of magnitudes, like start with like 1 microsecond, 10 microseconds, so on and so forth to, yeah, a millisecond. Okay. You have a question, Sophia?
Yeah, so when you're, if you don't know the time, characteristic time, and you're looking at those ranges, different ranges, how would you know, what would tell you when you have like a good width that you're using?
Yeah, that's a really good question. So if you start to, if you are below that characteristic time, you should see no change in the instrument response function, that you should see a similar shape. So let's say it's a low pass filter type response where your instrument response function should be an exponential. As you test shorter and shorter times, you're always going to see an exponential, and maybe the overall magnitude of that will change, but you're always seeing an exponential. But if you have something that's longer than your characteristic time, when you do the convolution, you're going to start seeing effects of the length that's taking place there, that you're going to see that exponential convolved with the extra signal that it's able to respond to that's slower. So if you work through the MATLAB modeling portion of the convolutions, you'll start to see that show up, that it's going to be able to respond to those longer signals there. So that's what
I'm not sure I understand what happens when it's above the time of the characteristic time. Could you explain that again, please?
Yeah, so when it's above the characteristic time, it will actually be able to respond. Like the characteristic time, let me think of the best way to put this. If you send something faster and faster and faster in, you'll always get that instrument response function out. But if you send something that's slower, it will be able to respond to the start of the signal. It will be able to respond to the middle of the signal that you're sending in, and will be able to respond later on in the signal. So you'll start to see, when you take that convolution, you'll start to see it be able to spit out the signal that you're putting in. So you won't get just the instrument response function back. So like, so we define this as our convolution. And if you send in a delta function or anything that is shorter, your delta function has to be shorter than your instrument response function here. If you send anything out that's shorter than that, your output is going to be your instrument response function in time. But if it's greater than that, if you send something that's, then this can't be approximated as a delta function. Okay, like I understand mathematically, like I'm not writing this in the clearest way. Maybe I should define this as like your test. Let's call this like the test signal, like capital T. If your test signal is greater in length than your instrument response function, it can't be approximated as a delta function. And what you're going to get is some convolution of your test signal and that instrument response function out. So because your instrument can respond to that longer signal.
I understand now. Thank you.
Okay. Any other questions? Okay. So I showed this plot over here as something that you might realistically use in the lab, where based on whatever circuit you construct, if the time constant is less than 20 microseconds, 10 microseconds, this type of instrument response, this type of delta function approximation that you can produce with your ARB is very short, a burst, square wave burst here. That's going to be shorter than that. And maybe if your expected characteristic time is 10 microseconds, this might be a little bit too long, but again, you need some area underneath here to then overlap with your instrument response function to produce some type of output. So that's why it has this like pretty high, nice voltage of 2 volts. And I'm working with 5 microseconds instead of 1 microsecond or 10 nanoseconds, where that area would decrease and you would have less of an output to observe here. Yeah, so tomorrow in lab, you'll probably be, this section will be walking you through different ways to get the frequency response function and the instrument response function. And I first just want to sketch this out, that for your low pass filter, what you're really doing is convolving a delta function with your exponential function for the instrument response. So what this visually looks like would be just a quick cartoon that you have your delta function, you're convolving that with your exponential decay, and what your output would be. So this would be your IRF, this would be your delta, and then what your output would be in time would be the convolution, just like that cartoon I showed, where you would see the decay over here. This is where it's just starting to overlap. And then once it completely overlaps, you see the decay, and you can then fit this to get your time constant. And then if you take the Fourier transform, you're able to then get that half a Lorentzian shape for your output and frequency to then quantify your frequency response function. So this is like the first method that you can use, where you would send a delta function in time. To get your instrument response function in time. And then you would take the Fourier transform to get your frequency response function. So that's one method that you can use. You'll also explore two other methods that are also possible. You can send a sine wave input in. And you're going to have a constant, you're going to keep the amplitude constant. In your input, and then you're going to vary the frequency. And then if you plot the change in your amplitude for the output, versus the frequency you're sending in, you can then get your frequency response function. So you produce a plot where you'd have frequency and your output amplitude here to get that out. So this is another way that you can get your frequency response function. Yeah. But it's a very slow process to do this. Less mathematically involved, but very slow, that you're really varying this frequency by hand. Then the third way that you can determine your frequency response function is to use white noise, because white noise represents all of the frequencies equally, what you guys found in lab 2. So that's a quick way to, instead of sending frequency one at a time with the sine wave, you can send all the frequencies at once using white noise. The output of the noise would then have your frequency spectrum present. So your output in time, take that Fourier transform, and it will show you which frequency components have been removed. So these are 3 different ways that you can get your frequency response function. In the lab, you'll explore all of those. And depending on your instrument, depending on what your setup is, some of these are easier to do than others. Okay, any questions with that?
I have a question. So we keep saying that, like, for the Fourier transforms, we can't ever really have continuous data because there's time between samples and things like that. Is it and also similarly, like, this delta function can't be exactly a delta function, so the Fourier transform wouldn't exactly just be a horizontal line. Does something analogous happen with white noise? Like, when you press white noise on the ARB or whatever, and you send that into whatever you're measuring it on, does that really have all frequencies? Like, does it really have that power spectrum that's constant, or is that also kind of an approximation because it's real life data?
Yeah, so there's going to be an approximation there as well. And I think I was talking to you in the lab that, like, our user manual does not have a good definition for what their white noise is. And that's something that I guess the lab as a whole should look at, if we can find in the manuals or documentation if they define what frequencies are present. But I think if we looked at the specifications for the ARB of what frequencies it's able to produce, that's what I would guess would be the frequencies that are produced by the white noise. But yeah, it can't produce all frequencies, but for within the certain range that the ARB works, it'll produce these frequencies in the white noise spectrum. But yeah, that's a good question that you always need to know, like the limitations of the instruments that you're using. Okay. So a little bit of shift. We're talking about frequency response function. A little bit of shift, talking about some math as well about the power of convolution, and we'll get back to the instrument response function. But I want to give an example first, a mathematical example of like how you can evaluate convolution quantitatively, because we've been really talking about it with like sketches, using it with just the delta function for an approximation, but we haven't really given a mathematical example of working with convolution. And I want to give an example of if you have two Gaussian functions, where we're going to call this one Gaussian A, where we're going to say it has some amplitude, and we're going to write this in time. And it's going to have some width sigma A squared. Okay, let me check the chat. Okay. We're going to convolve that Gaussian with a second Gaussian. We're just going to call it GB. Has some amplitude, capital B. Again, just writing out the Gaussian equation. Where the width of these Gaussians, again, is going to be defined by the sigma that's in the denominator there. And I'll just sketch out Gaussian B with a wider width there. And if we want to convolve these two Gaussians, we can do the whole integral that we wrote out and evaluate that. But if we remember back to what we defined, that if you have a given function and you're taking given two functions and you're taking the convolution, it's equivalent to taking the Fourier transform and multiplying the Fourier transform of those same two functions in the frequency domain. So it's going to be much easier if we take the Fourier transform of these Gaussian functions and take their product instead. So if we want to do that, do you guys remember or recall what the Fourier transform is for a Gaussian function?
Another Gaussian.
Yeah. So we can do that with a different width. So I'm going to quantitatively write what the Fourier transform of these, and we're going to ignore the amplitude just to keep this simple. That then for Gaussian A, we can write this instead as ignoring the amplitude, e to the negative omega squared over 2 times, it has the inverse width, if you guys remember, 2 times 1 over sigma A squared. And we're going to multiply that times Gaussian B in the frequency domain. Its Fourier transform is going to be very similar notation. So if we take the product of these two Gaussian functions, what we're going to get is the following. Where the frequency and the two remain, we're just summing those two together. We can then flip these terms that are in the denominator. It's going to be equivalent to e raised to the negative omega squared, sigma A squared plus sigma B squared, all divided by 2. And then if we take the Fourier transform of this to then get this in the time domain again, that just will flip those sigmas, and we're going to get the following. This should be time. Sorry about that. So what we can see is if we convolve two Gaussians here, what we get is another Gaussian out, but its width is going to be the sum of the square. The new width of that Gaussian after the convolution is the sum of the squares of the original Gaussian width. So we can say that new width is going to be some of the squares and the square root. That I forgot to include in there. So you may have seen this type of equation show up when you're working with error propagation, or if you're adding normal distributions, taking products of normal distributions together. So if you're propagating error, if a certain data set has error sigma A, another one has sigma B, if you're working with those, this would be your new error there. So this is just showing you this worked example with Gaussians. I'm mentioning it's important for error propagation, but also the power of working with Fourier transforms and taking the product of the functions in frequency space to then understand this in the time domain here. So this worked example of how you can quantitatively work with convolution. We can then use that when we're working with the instrument response function as well. If we only want to resolve the real signal, if we want to remove the component or the contribution of our instrument. And this process is called deconvolution. So if we want to do this, we can write out our output again. And if we define convolution based on this integral, that this is what we're defining as the convolution of our signal in the instrument response function. And we can also say that our output and the convolution of these is equivalent to taking the Fourier transform of the product of those in frequency if we look at this and we want to remove the contributions of the instrument response function or the frequency response function, given this equation here, what do you think would be the easiest way of removing the IRF from our output? Do you think it would be easier to work in the time domain or the frequency domain? To deconvolve or to remove the effects of that IRF? So we can work in the frequency domain. If we focus on this side of the equation here, the easiest way to make omega s equal omega, our signal be equivalent to the output would be dividing by, in frequency to space, the output by the instrument response function. So if we take and divide our instrument response our frequency response function from the output, what we would be left with is just our signal. And then we can take the Fourier transform of that and just only get our signal out. This is what I meant by like just having the real signal is just having S of t here. So this is what we mean by deconvolution. So that we can divide this out and then get in the time domain. And the power of using convolution mathematically in the frequency space. But it's very important to know that deconvolution doesn't always work. And it doesn't always work because of the effects of noise or uncertainties that you have. That deconvolution only works if you know your instrument response function extremely well. That if you don't have this extremely well characterized, if there's noise present, you'll see artifacts showed up. And I see this in my own research where we're trying to do deconvolution in our microscopy images, and you'll see sampling art, you'll see artifacts show up if this isn't done right. And deconvolution, here we described it very simply with division, but if you're doing this over space or over all time, it can be a little more complicated. So MATLAB and Origin do have built-in functions. In a way, so you can do this in a linear process or a nonlinear process as well. So any questions with deconvolution at all?
So is deconvolution something that we would do like mathematically afterward, or is there a way to do it physically with the signal?
Yeah, typically it's something that you do in post-processing. I would think that maybe some commercial instruments, very fancy instruments, could do that within their like black box type setup. But it's typically a software type process. You're not going to do that in a hardware way with circuitry, since that circuitry itself will also have its own response function as well. So it's usually a post-processing of your data. Okay. Any other questions? Okay. So,
Also,
yeah.
4-minute mark.
Sorry?
4 minutes. Sorry, 4-minute mark.
Yeah. In interest of time, I want to get through this last part. Just to mention some other some limitations that we've talked about: low pass, high pass, and band pass. That they're analog. They're also passive. There's no power requirements. And how we've sketched these instrument response functions and frequency response functions, they're very far from ideal. That, like for a low pass filter, an ideal low pass filter would have an instrument response function that would look something like this, that you get 100% pass through, if this is frequency here, and 0% pass through at lower frequencies. But this isn't what you're actually able to do. And you've actually seen artifacts from this show up in the lab, and I'll upload some notes about this, that with the DSO, and I saw a lot of this in your data in the last lab report in lab 2, that for a square wave input, you have amplitude versus time here. You zoomed in, you would actually see some oscillations here. at the edge of your square wave, because the DSO is actually acting as a low pass filter with a 10 megahertz cutoff. And this phenomena, this observation is actually called the Gibbs phenomena. And it was actually observed first at Case Western by Michelson, but he wasn't able to describe it. But Gibbs was able to describe it, hence why he got the name on it. And if we had more time, I'd go into the history of that. But I'll upload some notes a little bit about this Gibbs phenomenon. But this is what you would see when something is far from ideal or not ideal, that you actually see these artifacts show up. So that's why there are alternative filters that you may run into. Some of those could be, you'll hear terms of like a Gaussian filter, Bessel, Butterworth, all named after likely the old white guys who developed them. And they have different band and stop pass regions and phase responses. And these would be other analog filters that you may encounter when you're working with electronics in the future. You also may run into active filters. And these would include a power supply, use op amps in addition to resistors and capacitors or inductors. And these typically, because they have a power supply, they'll have better performance than the passive filters that you guys have been using. So I'll also upload like a sketch of just an example of an active low pass filter that does use a power supply with an op amp as well. And then finally, you might also run into digital filters where there's A to D or D to A conversion, which you guys all covered, I think, in last fall, hopefully in your courses. And you can perform your filtering in the digital domain instead of the analog domain as well. So those are some things that you may run into in the future with filters to get closer to this ideal where you have a nice, beautiful cutoff instead of like this slope that we're seeing and a change and a transition between what's being filtered and what's being not. So I think that's most of everything.